All right, welcome to the second lesson. It is called Electron Half-Reaction. So before, when we were looking at reactivity, we looked at our activity series to help us figure out if a reaction was going to happen. So let's put some zinc electrode, some metal zinc, solid zinc, into a copper sulfate solution. So we know that copper sulfate, CuSO4, is soluble because it's aqueous. So that means when it goes into solution, it's going to form a Cu2 plus ion, and it's going to form an SO4 2 minus ion as well. So in solution, what we'll find is that the SO4 doesn't really interact with the zinc so much. It will remain aqueous, but there is an interaction between the zinc and the copper 2 plus. Now, the activity series will help us figure out what that interaction actually is. So if we look at our activity series, which is just here on the side here, this is for our metals and this is for our non-metals, what we can see is that there is an interaction between zinc, which is right over here, and copper, which is right over here. Now, because zinc is higher up on the activity series than copper, what that means is that zinc is more reactive than copper. So when you put a piece of metal zinc into a copper sulfate solution, what zinc is going to do is it's going to displace it. Okay? It's going to displace the copper from the solution. Now, what does that actually mean? What does that actually mean, that zinc is going to displace copper? Well, if we look at zinc right here, like that, and you have Cu2+, what it's going to mean is that zinc is going to push copper out of the solution, making copper Cu solid, and making zinc Zn2+. Well, if you remember from the last PowerPoint, we saw there was a relationship where you had a solid and an ion on the left side of the equation, and then they switched. It's still a solid and an anion on the right side of the equation, but the species that were the respective solid and ion changed. Well, what we see here is that we're actually having a redox reaction. So this is just a kind of demonstration of what is actually happening. So what you can see here is that here we have a solid strip of zinc, and we're putting into this kind of blue copper sulfate solution, copper 2 sulfate. And eventually, this zinc is going to start gaining some kind of material deposit on top of it. And the blue color of the solution is also going to decrease. The material that is gained by the zinc is actually solid copper that is being deposited on top of it. How does that work? Well, if we're looking at our actual diagram here, what we can see is that here's a strip of zinc. This is the zinc electrode placed in. And you can see that the zinc is interacting with the copper that is in the solution. It's a copper 2 plus right now. And in this case, the zinc right here, okay, the zinc right there, is more reactive than the copper, so it's displacing the copper out of solution. How does it actually do that? Well, this little diagram actually gives us a pretty big hint. It forces electrons onto it. So in this case, what's actually happening, and let's just draw the whole equation here, see if we can come up with an idea of what's actually happening. We have zinc solid plus CuSO4 aqueous, and that's reacting, and zinc is being pushed, is pushing copper out of the solution. So copper is being formed, copper solid plus zinc sulfate, SO4. All right. Well, if you remember, this is called our molecular formula, okay, from grade 11. This is our molecular formula. Now, we can actually get rid of the spectator ions, or, well, first we can see if there are any, by first forming the total ionic formula. The total ionic formula, or the total ionic equation. And that's just done by breaking up all the aqueous parts into their respective ions. So zinc is a solid, so it's going to remain as zinc solid, plus Cu2 plus, and that's going to be aqueous, plus SO4 2 minus, and again that's aqueous, gives you solid copper plus, we're just going to write it here, zinc 2 plus, and SO4 2 minus. Now what we can see is that the SO4 2- is on both sides of the equation, so we can actually cancel those out. Those are our spectator ions. So if we cancel those out, what we're left with is we're left with our net ionic equation. So in this case, our net ionic equation is our zinc solid plus our Cu2 plus aqueous, and that gives rise to our Cu solid plus our zinc 2 plus aqueous. So that's actually what's happening in this reaction. Okay? Now, what we can try to figure out is what is actually happening. Is this a redox reaction or not? Well, let's see. So if we look at our zinc here, if we look at our zinc, what we can see is that it doesn't hold a charge. So that means we're just going to assign a charge of 0. For the copper itself, what we'll find is that here we have a 2 plus charge, so we'll write that down, 2 plus. Same thing for the copper. Copper has no charge, so it has a 0, and the zinc, we see that it has a 2 plus. Now, if we just connect these, let's connect these. Let's connect the zincs together. Here we go. There's our connection there. And let's connect the coppers together. Now, let's try to figure out what is actually happening here, if there is anything happening, to start with. So, let's look at our zincs. Our zinc is going from a charge of 0 to a charge of 2 plus. So, what's actually happening is that it's becoming more positive. Now, how can it become more positive? The only way that it can become more positive is by losing 2 electrons. It's going from 0 to plus 2, so it's becoming 2 times more positive. So that means it must have lost 2 negative things. The only things that are negative and that can be lost are 2 electrons, so it's lost 2 electrons. On the other side, copper has gone from 2 plus to 0, so it's actually become more negative. And the only way that it's become more negative is that it's gained those 2 electrons. So what's actually happening in this solution, the reason that zinc is displacing copper is because zinc is forcing its electrons onto the copper 2 plus ion. So in this case, what is happening to zinc? Is zinc being oxidized or is zinc being reduced? Well, if you remember our definitions, something that loses electrons is oxidized. Okay? So in this case, the zinc is becoming oxidized. And the Cu2 plus, because it's gaining electrons to become the Cus, this is being reduced. Now this is a huge mumbo jumbo, and as you get practice, you'll be able to get this a little bit easier. But there's an easier way to try to get this, and this is using half reactions. Let's just summarize what we just talked about. Slide. So here we have our zinc solid. We had our copper 2 plus ion and our sulfate ion aqueous. Because we saw the sulfate on both sides, those were our spectator ions, so we crossed them out. Okay, so we can get rid of these, because they're both our spectator ions. Remember that they don't really participate in the reaction. When we looked at the zinc went into a 2 plus state from a 0 state, so it must have lost 2 electrons. Because that happened, zinc was oxidized. Okay, and that also means that it is the reducing agent. It forced the copper 2 plus to pick up the 2 electrons that it lost. And if we look at the comparison between copper 2 plus on this side and the copper here, we see that it goes from 2 plus to 0, so it's become more negative. It gained those 2 electrons, so it became reduced. And that also means that it was the oxidizing agent. So to get a clearer picture of what's actually happening, we can split the entire reaction into these 2 half reactions called electron half reactions. So remember from the first presentation, you can't have an oxidation reaction without a reduction reaction. And so one of them will be a reduction reaction. Okay, so that will be the species gaining electrons. And one will also be an oxidation reaction where the species is losing electrons. So here are the steps to determine the half reactions. You can just pause it to write this down, or you can just copy it from the PowerPoints provided as well. All right, so let's do an example of what we just saw there. So our example here, we have solid aluminum reacting with 3 moles of silver nitrate, aqueous. to produce aluminum nitrate and 3 moles of silver. Alrighty, so in this case, what we're seeing is that the aluminum is displacing the Ag. So let's take a look and see if we can break this up into our 2 half reactions. So I'm just going to make this a little bit smaller, just so we have a little bit more place to work with. Alright, so let's take a look and let's see what we have. Now the first thing we want to do is we want to break this molecular formula into a total ionic formula. And the way we can do that is again by splitting up the aqueous solutions. So here we have aluminum, and that's in solid phase, and we're going to split up this aqueous solution of silver nitrate. So we have 3 silvers, Ag, aqueous state, and we know that each one is plus because we know that from our periodic table. And then we also have 3 nitrate groups, 3NO3, and those are all aqueous. Okay, and they have a charge of -1. All right, sweet. Next thing, there's our arrow. Doesn't look like a very good arrow over here, actually. Let's try that again. Let's go for perfect here. There we go. So we have an aluminum atom, Al, and has a charge of 3+, and it's in the aqueous state. And then we also have 3, because we have a subscript there, we have 3 nitrate groups, NO3- in the aqueous phase. And finally, we have 3 solid silver atoms created there. Okay, so that's our total ionic equation. Now let's look for some spectator ions and see if we can cross some things out. So again, we're looking for things that are on both sides of the equation in equal amounts and in the same state. So what we see is that we see our nitrate ions on both sides. We can cross those out, and now we're ready to write our net ionic equation. So our net ionic equation, just simply what we have left over. So we have Al solid plus 3Ag plus ions, the aqueous, and that gives us Al3 plus aqueous to produce 3Ag solid. Alrighty, so that is our net ionic equation. Now what we want to do is we want to break these up with the same element in mind. Okay, so in this case, we're going to break it up, the same element being, for example, Al here and Al over here. So I'm just going to break it up into two parts. So my first one is going to be Als, and that's going to be an arrow pointing to the Al3 plus ion, aqueous. My other half will be our 3Ag plus aqueous, and that will form our 3Ag solid. Okay, so what it says in the second step is that we need to divide each equation with the whole number that gives us the smallest the coefficient. So the ALs, they're already at 1, we don't have to do that. But the AGs, we have to do that step because we see 3, we have 3. We can break that down a little bit further by dividing by 3. So if we divide everything by 3, we'll get Ag plus aqueous, and we get 3Ag, we divided by 3, so we can get rid of that 3, and we get Ag solid. Alrighty, so we're there. Now, what we want to make sure is that we want to add a sufficient amount of electrons so that the charge on both sides of the equation are equal. Alrighty, so in this case, if we look at our aluminum first, here on this side we have a charge of 0. There's no positives, there's no negatives, but here we have a charge of +3. So we have to get rid of that charge of +3 somehow, because we can't really just remove electrons from something here. So what we're going to do is we're going to do this. We have Als, Al3 plus aqueous. Now to get rid of that 3 plus, we can add 3 negatives. And what are 3 negatives? Well, 3 electrons. Now to do the same thing for the silver side. So on the silver side, on this side, we have a +1 charge. On this side, we don't have any charge whatsoever. So again, we want to get rid of that 1 plus charge. How can we do that? Well, we can add an electron on this side to get rid of that positive charge. So what we can do is we get Ag plus aqueous, we add 1 electron, and we create Ag solid. Okay? And that's it. We have our 2 half reactions. We have our aluminum half reaction, and we have our silver half reaction. Now, which one is this? Is the aluminum oxidation or reduction? Well, let's see what actually is happening to our reactant aluminum. what we can see is that aluminum has no charge here, and it becomes more positive. Now, for it to become more positive over here, it would have to lose these electrons. So in this case, what this is over here is that this is an oxidation. Aluminum is becoming oxidized, and aluminum is also our reducing agent. On the other side, what we can see is that the Ag plus is gaining an electron. So if it is gaining an electron, this is going to be reduction. Ag plus is being reduced, and that means Ag plus is also our oxidation agent. So take a moment and try to figure this out. The example is magnesium powder heated with copper 2 oxide produces copper and magnesium oxide. So figure out what the total molecular equation is, and then break it down into the net ionic equation, and we'll be right back. All right, so welcome back. These are the answers for our total molecular equation. We have solid magnesium reacting with copper 2 oxide, so CuO, producing copper and magnesium oxide. Now, our net ionic equation, what we found was that the oxide atoms, O2 minus, were our spectator ions, so we got rid of them, and we were left with our net ionic equation. Now, in this case, so here we have our Mg plus Cu2 plus, gives you Cu plus Mg2 plus. Try to figure out which one is the oxidation half reaction and which one is the reduction half reaction, and we'll be right back. All right, so here we go are the answers. We can see that the charges that we have of Mg and Cu2 plus, 0 and 2 plus on the top here and the top here. And again, this Cu doesn't have a charge, so it's 0, and here we have a 2 plus. So if we looked at Mg, it went from 0 to 2 plus. That means it's become more positive. That means it must have lost electrons. How many? Well, it became 2 plus, so it lost 2 electrons. Copper had a charge of 2 plus, and then it became 0, so it became more negative, and the way that it became more negative is by gaining 2 electrons. So in this case, if this has lost the electrons, that means that this is the oxidation reaction. So Mg went to Mg2 plus, and it's lost 2 electrons, and the copper 2 plus ion gained 2 electrons to become copper metal. So try to figure out, based on that example, which one is undergoing oxidation, which species is undergoing reduction, which is the reducing agent, and which one is the oxidizing agent. So just pause, and we'll come back when you figure that out. All right, welcome back. These are the answers here. So oxidation, magnesium is undergoing oxidation because it's losing 2 electrons, and Cu2 plus is undergoing reduction because it's gaining electrons. Now, because Mg is becoming oxidized, that also means that it's forcing Cu to take its electrons. So that means that it's also the reducing agent. And on the flip side, because Cu2 plus is gaining electrons, that means it has to forcefully take them from somewhere. And so it's taking them from magnesium. It's forcing it to be oxidized. So Cu2 plus is going to be our oxidizing agent. And finally, what we know is that redox is all about the movement of electrons, and they have to be transferred from one to the other. Well, how are they transferred in this example? Well, once again, if we remember that magnesium is losing the electrons this way, and it's forcing the electrons onto Cu2 plus, which himself is becoming Cu. So what's actually happening is that magnesium is moving its electrons onto the copper. So Mg is forcing its 2 electrons onto the Cu2 plus. When it does this, Mg becomes Mg2 plus, and Cu becomes Cu. So in the direction of travel is always from the species that is being oxidized to the species that is being reduced. Okay, and that makes sense, because oxidized is about losing electrons, and this is about gaining electrons. So you have to first lose them in order to gain them. So in this case, it'll be moving from magnesium to copper 2 plus. Now this is the basis for spontaneous reactions in batteries. This is how batteries work. So to understand, we need to understand that it always moves from the oxidized species, the one that wants to lose its electrons, to the reduced species, the one that wants to gain electrons. That's it for this one. See you in the next lesson.